ready to start, I don't have to write. You started? I was just writing this.
Yeah, we can start.
Oh, okay. Hi. I'm Dan Freed. Thanks, it's a pleasure to speak to you all again. So I picked a rather old topic today. Topic of parallelism, something that we all learned about in preschool, I imagine, high school geometry. And I want to tell you a little bit about parallelism and use it to introduce some kinds of geometric ideas and settings in which we do geometry. So we'll see how far we get. And so the story starts with Euclid. And this is about 300 BC, so that's about 2,300 years ago, something like that. So it's a long time ago, and well, we all studied Euclid in high school, probably not from the original Elements, but the Greeks had amazing achievements in kind of modes of thought that they invented to study mathematics and the ideas of making postulates and making undefined terms. Maybe they didn't recognize quite undefined terms and theorems and so on. And Euclid had what came down to us as basically 5 basic postulates for geometry, and the 5th one was this rather elaborate one concerning parallelism that I wrote the first half of. And so I'll read you the rest so that I don't spend the time doing that. It says that if a straight line falling on 2 straight lines makes the interior angles on the same side less than 2 right angles, the 2 straight lines, if produced indefinitely, meet on that side on which the angles are less than the 2 right angles. Is that clear? So, I guess what it says is the following, that we have a straight line like this, and we have 2 straight lines like so. And what he's saying is that the 2 angles that are formed on the same side are less than, each one is less than a right angle. And then what the postulate says is that eventually, if you extend these indefinitely, was the word in that translation, then these 2 lines will meet in a point. So Euclid and the Greeks at the time didn't really have the notion of infinity, whether it be infinitely large or infinitely small, and so didn't want to talk about lines extending in a kind of infinite plane. They also didn't want to talk infinitely small about irrational numbers. So there are a lot of elaborate constructions in the Greek mathematics about rational numbers and so on, and they knew that there exist irrational numbers, but that wasn't something they could wrap their head around, because again, that involves some kind of infinite concept. So that had to wait until 16th, 17th century for mathematicians to tame infinity. But this is the parallel postulate that when David Hilbert, German mathematician, many years later, just before the turn of the 20th century, he wrote a book about a kind of modern version of the elements, about the foundations of geometry. And in his version, that postulate says, let A be a line. So we have a line called little a, and let capital A be a point not on that line. And then he says, there exists at most one line through A. So there exists at most one line through that point A that doesn't meet little a. And in Euclidean geometry, there's exactly one such line, and that's the usual form of the parallel postulate. If you have a line and a point not on the line, then there's a parallel line. Parallel means controversial postulate long ago. And even from the beginning, that people recognized that that looks quite different from the other postulates that Euclid had. And so they tried to address it in various ways. One was to make a simpler postulate from which they could prove this parallel postulate. And another one was just straight out prove the parallel postulate. Just drop it from the list of postulates and try to prove it from the other postulates. So there were people in Euclid's day, Proclus, Ptolemy, and so on, who tried to do that. They claimed too that they made mistakes. That continued for more than 2,000 years. English mathematician Wallace, you may have run into him. In calculus, he wrote about that. Saccari, Legendre, all sorts of mathematicians wrote about it. And eventually, it was discovered at the beginning of the 19th century, the 1800s, that in fact, the parallel postulate can't be proved from the other axioms because there exist other geometries that satisfy all of the axioms, have all the undefined terms, a point and line, and so on, and satisfy everything else, but don't satisfy the parallel postulate. And those are what were called non-Euclidean geometries. So those were discovered by Gauss, by the Hungarian Bolyai, by the Russian Lobachevsky. In fact, Bolyai's father was a friend of Gauss's, and he wrote to Gauss in about 1820-something and said, you know, my son has made this fantastic discovery, and so on. And Gauss wrote him back and said, yeah, it's wonderful. I actually thought of it 20 years ago. But that was Gauss for you. So, okay. So that's the kind of story of the parallel postulate in quick. And so I want to put parallelism in the context of a kind of point of view of geometry that's due to Felix Klein, associated with him. Another German mathematician lived in the time of Hilbert, also worked at the same place in Göttingen, Germany. And he had something called the Erlangen program. And he said that geometry is the study of properties invariant under a group. So he put the idea of a group of symmetries, as primary in studying geometry, and that the geometry should be specified by telling what the group is, and then you study properties invariant under that group. So for example, when you studied Euclidean plane geometry in high school, did you study it from the point of view of a group? No. There was an effort to do that in the curriculum, I must say, a while ago. I was just trying to find out how much that penetrated the curriculum. Well, surely you talked about things like reflections and rotations and translations. And you probably discussed the concepts like length and angle and area, congruence of triangles are invariant under those kinds of symmetries. Right? So length, angle, area, those are all concepts in Euclidean geometry. And from this point of view, those are in Euclidean geometry because there's a group called the Euclidean group. And those are invariants of that group. Those are properties that don't change when I apply that group. And so I want to say that if we want to study parallelism at its most basic, then from this point of view, we want to identify a group of symmetries that is a symmetry of parallelism. And in fact, a symmetry of the geometry of lines. So, so what groups do you think that is? We want to study lines. What's the kind of most basic group we might study where we would move lines around?
Affine group?
Affine group would be, yes. But there's an even smaller group we could use, a subgroup of the affine group. What's that? Don't be shy.
The orthogonal group?
Orthogonal group the orthogonal group is a smaller group, and, well, it's going to have more invariants. The orthogonal group is also going to preserve length and angle concepts like that.
Plus
Translations. So in fact, I just want to use translations. So I want to study a geometry at the beginning where we just have the translation group. So let me just review a few concepts. So if G is a group and X is a set, then does everyone know what it means for the group to act on the set? So the group acts on the set means that we have a map, say it acts on the right, we have a map like this, given a point P and an element G of the group, we get a new point on the set. So there's some map like that, and it has to satisfy the property that if I act consecutively by two group elements, that's the same as acting by the product of those group elements. So that's what we mean by realizing an abstract group G as symmetries of X. That's a map from G into symmetries, maps from X to X, which are necessarily invertible, bijective. So that's how we realize a group of symmetries. And so here's the definition. Let G act on X. I made it a right action. Then X is a G torsor. So here's a new word, potentially a new word. If the action is simply transitive. So what does simply transitive mean? Well, I have some set X, and I have some group acting on it. So there's some group G acting on X. And imagine that I have 2 points, P and P prime. Then saying it's simply transitive, well, that's 2 statements, simple and transitive. The transitivity says that I can write P prime equals the action, the result of acting by G on P. So that's the transitive action. We can get from any point to any other by a group element. And the simple means that this G is unique. So every non-identity element moves every point. Okay. So that's called a simply transitive action. Sometimes it's called a principal homogeneous space, but torsor is a rather shorter word for it. Question?
Yeah, why does it have to be the non-identity?
Well, the identity element fixes every point.
Oh.
When you have a group action, the identity element has to fix every point. Okay? Okay. So, yeah. So that's called a G torsor. And so now we want to think of translations as a group. Yeah.
Sorry, you don't need this action to be faithful.
Right. Well, it is faithful because I said that every non-identity element moves every point. Faithful means that every non-identity element moves some point.
Did that follow from the simple?
Yeah. Yes. But again, this one, every non-identity element moves every point. And being faithful says that every non-identity element moves some point. So this is faithful with a vengeance. Okay. So you can think of X as like a copy of the group, but without an identity. A group is a structure that's a set and a point, the identity element. Here we don't have a point kicked out. Okay. So what is the translation group? So we're going to start. Yeah. Sure.
I'd find there after so you can
Find a natural stopping point. Okay. Sure. All right. So I want the group G to be a group of translations. So abstractly, what is the group of translations? How does it look like? It's an abstract group.
Rn.
Rn. And Rn means what?
N relation of n product of n product of real life.
Okay. Well, what structure does it have? What's the group operation?
Addition.
Addition. So it's a vector space, in other words. Okay. So we're going to take our group of translations to be a vector space. So let B be a vector space. And then the definition is that an affine space A, and we might say over B, is a B tensor. So an affine space is a space on which a vector space acts simply transitively by translations. So if I want to draw a picture of an affine space, it looks like this. And there's an associated vector space. I'll draw in red. And the vector space is a group. So the vector space has an identity element. That's the zero vector. Right? So if you remember the axioms for a vector space, there's always a zero vector. And if I give you a vector in the vector space, then, and I give you a point in the affine space, then we can always take that point and translate by that vector. And the result, well, we write a plus sign here rather than a times, because V is abelian, it's a commutative group. And the result is the translation of the point P through the vector psi. So that's what an affine space is. And of course, we have an addition of vectors, but we don't have an addition of points in the affine space, and there's no base point. So if you want to think of a kind of real-world model, just think of the one-dimensional case where you might think of the vector space V as being, well, as being something about time, and the affine space are really points of time. And if you want to know the distinction, then it's really different for me to say that this talk will end at 6 o'clock, or this talk will end in 6 hours. So 6 o'clock is a point on the affine space, and 6 hours is a translation in the group of time translations. It's in the group. Yes?
On that note, is there a good part or good time for us to get pizza or no?
Well, you said at 5:20, right?
Yeah.
So that's either an hour or 2 minutes, depending on how your affine space. Okay, well, do I wait for the pizza man to come in? Or do we break now?
We can break now.
All right, well then I'll give you something to think about. So the thing to think about then, while you're eating pizza, before I start again, is now that we have this fairly simple definition, but I'm using a modern context where we know what a vector space is, right? So I'm using that, and now we want to go back and define, first of all, what I mean by a line, because we want to talk about parallelism of lines. So tell me what I mean by a line, an affine line, meaning a line in this affine space, and then tell me a definition for what it means for two lines to be parallel in terms of this structure where I have this group of translations. So I'm doing everything in terms of the group. All right, pizza. There is no pizza? Tell me to break. All right. Does anyone have any ideas about how we're going to define a line in A, this affine space? So I hope the pizza gave you energy to put you to sleep. Yes?
Is it going to be the orbit of some point under the action? Oh wait, no, it wouldn't be.
Well, in
The
the general
other
course,
subspace.
or what is the orbit of a point?
It's going to be everything. But
Right.
so
Well,
if you take like
arbitrary.
if you take like a subspace or a,
Ah.
and then you look at the orbit under something that spans it, a one-dimensional subspace. Well, I mean, yeah, it doesn't.
Okay. So a one-dimensional subspace of
V.
V. So we're going to lean on the fact that we know notions from linear algebra about vector spaces. And in particular, we know what it means to be a subspace. Right, subspace. So, by the way, I didn't say anything about what field I'm working over. And we could work over an arbitrary field, but we're picturing it over the real numbers. And I didn't say that V is finite dimensional, so we could have V even infinite dimensional. But however we resolve those questions, that's defined according to what was said. A line in V is a one-dimensional subspace. So that's a line in a vector space. And a subspace is a subgroup under addition. Okay, very good. And now we'll define an affine line. L in A is, what did you say?
It's the orbit under the action of the elements in that subspace.
Right. So it's the set of points of the form P plus L for some P in A. So I take a point in A. P, and I take the orbit of that point under that subgroup, which concretely means that I take all vectors C in this line, this one-dimensional subspace, and I take all the translates of P by those vectors, and those sweep out an affine line. So that's the definition of an affine line. Very good. So now we know what a line is. And so what does it mean for two affine lines to be parallel? So L prime, affine lines are parallel. What?
They come from the same end.
What's that?
Just different points, same end.
Different points, same L. Exactly. Well, we could have another point here. We could have described this line as P prime plus L, perhaps. But what would that tell me about P and P prime? If they describe the same line, how do I get from P to P prime? I get there by a unique vector. That's what the Torser condition tells us. And what would we know about that vector? P and P prime are on the same affine line. That vector is in this vector line, L. Yeah. So they're parallel if, well, we can simply say that L is equal to P plus L, and L prime is some other P prime plus L. So the same L for some P and P prime. So that's what we mean by parallel lines. Yeah. So now this parallel postulate, of course, becomes a theorem in this geometry, right? Namely, this statement in the form that Hilbert said it here is a theorem, right? So, given our affine space, if we have a line in that affine space, sorry, the colors got mixed up, but anyway, if I draw the line like that, and I give you a point P, not on the line, then the theorem is there exists unique affine line through P parallel to the given affine line L. So I'll let you think about how to write down fairly easy proof. So this affine geometry certainly implements this Euclidean parallel postulate. And notice that there's no notions of distance or angle or inner product in this geometry. All we have is this group of translations so far. So the whole geometry is controlled in this Kleinian sense by this group of translations. Translations take lines to lines, and they take, in fact, parallel lines to parallel lines. If I translate, I'll get parallel lines. Not only that, if I translate a given affine line, I'll get a line parallel to that line. Right? So this group preserves the notion of parallelism. All right, so parallelism is something we do talk about in lots of contexts. This is flat geometry. That's why you might hear the word affine out of my mouth a lot of times, because affine geometry is flat geometry. That's the model that we have for any kind of geometry. So if we want to do some kind of curved geometry, like the geometry on a surface of a sphere or something like that, surface of a ball on a sphere, then we would model it by understanding geometry first in the flat space, the affine geometry. So that's the most basic kind of geometry. And other kinds of geometry, like Euclidean geometry and so on, are built from affine geometry. They're again flat geometries, but we'll come a little bit to say about that. So I want to make just a few comments about affine geometry and just show you some of the things. And let's start with one comment about parallelism. That's fun. So let's let L be the set of affine lines in A. So the affine lines form a set. And now the comment is that parallelism, so a little lemma, parallelism is an equivalence relation. On L. So that's again something you might try to prove. But any line is parallel to itself. Well, the line is P plus L. The line is P plus L. So it's clearly parallel to itself. That definition is manifestly symmetric, and you can see that it's transitive. So parallelism is definitely an equivalence relation, and therefore we get a set of equivalence classes. So let's let P equal the set of equivalence classes. And then there's always, when you have an equivalence relation on a set, we always get what you should think of as a quotient map. We get a surjective map that takes every element, that takes the set to a set of equivalence classes. It maps an element to its equivalence class. So anytime you have a surjective map, that induces a partition, an equivalence relation on the domain. 2 points are equivalent if they map to the same point under that surjective map. So even if it's not surjective, you get an equivalence relation on the domain. So you can always think of maps that way. And now I want to identify what is this P. So how do I identify that P? So when you're asked a problem like this, we just have not much data. What's our data? Our data is a vector space, this affine space over it. So the answer has to be just in terms of that. We don't really have much to play with. So how do I describe this set P? I describe this as the set of all lines in the affine space, so they're all affine lines. And what is P? What are the equivalence classes? Yeah.
One-dimensional subspaces of P.
Good. So, in fact, P is the set of lines in V, which we write as PV, which is called the projective space. V. Why is that? Well, every affine line has an associated line here in the vector space. If you like, we just take all the differences of points here, the translations that preserve this line, and that's a subgroup, a vector subspace of V. And that's a one-dimensional subgroup. So we can always map an affine line to here, and two lines are parallel exactly when those subgroups are the same. So we have a map from affine lines to vector lines, if you like, and that's a surjective map. So that's a way of slicing up the space of affine lines. So far, just a set. We haven't talked about a space. We haven't apologized it. And but still, thinking of the set, now we can ask what we would usually ask about such a map. Given L, which is one of these vector lines, let's describe line inverse of that. It's not a question, but I wrote it as a question because it's a question for you. So that's a little tricky. So let's try to draw a picture where this affine space, A is three-dimensional. and therefore so is the vector space V. And so in the vector space V, I fix a line, a one-dimensional subspace. You can think of it as a direction. And then what does pi inverse of that point here look like? Well, it's the subset of affine lines, which are all parallel to this. So it's a subset of lines that looks like this. But now you have to imagine that it's in 3 dimensions. Very well. Draw that. So that's some set of affine lines. And I want to say what that looks like. What structure does that have? So I may leave that as a problem for you to think about afterwards, because it will take a lot of the rest of our time to think about. But that's some space of lines that we have to be able to describe somehow in terms of just this data of the affine space, the underlying vector space of translations, this group, and this one-dimensional subspace. That's it. Well, if I ask you what that looks like, could you tell me, for example, what dimension that is? My ambient space is 3 dimensions, and I take the parallel lines, parallel to a given direction. How many parameters would I need to describe one of those lines? 2. So this should be some kind of 2-dimensional space. So one hint is that it's something 2-dimensional. Well, is it a curved kind of space? Is it going to look like this 2-dimensional sphere? What kind of shapes do I have in this game? All right, so we'll leave that one for after. But that's a fun thing that you might try to think about. Now, we could ask also, what is this? Well, we could ask, can we topologize these? Well, if we're working over a finite field, that maybe doesn't make a lot of sense initially. These are finite sets, if these are finite dimensional. But let's suppose we're working over the real numbers, where the real numbers has its usual topology. Then we can topologize this space of lines through the origin subspaces. We know what it means for 2 lines to be close, so we can also topologize these. And so we can ask, in a sense, what shape these are. For example, are these affine spaces? Are they flat? Well, think about the case when V is 2-dimensional now, and I'm asking, what does the space of 1-dimensional subspaces look like? What kind of shape is it? Well, the 1-dimensional subspaces are all of these. What kind of shape parameterizes those, would you say? A circle. You see, we might parameterize those by choosing some reference point and then measuring this angle, theta, between any other subspace and our reference subspace. And that angle runs from what? Well, it's 0 if we have the reference subspace. And then it increases, increases, increases. And by the time it gets to pi, I'm back to the reference subspace. So that angle runs from 0 to pi. That's just a closed interval. But 0 and pi are identified. So if I take a closed interval and identify the endpoints, I get a circle. And so you see, starting with flat geometry and just asking about parallelism, we've suddenly gotten away from flat spaces. We've gotten to something curved. So now you can try to think about what this projective space, this is called, looks like in higher dimensions. For example, if V is 3-dimensional, what does that look like? So, yeah. So in fact, I should say that we can, another thought journey for you, thought journey, I like that, is to explore the geometry of that projective space. So can you define in that projective space a notion of point? Clearly, in any space, we know what a point is. But can we define what a line is in this projective space? What do I mean by a line? What do I mean by a plane? And in fact, this is one of the non-Euclidean geometries that you can look up Euclid's axioms. And you could see that all of the axioms, once you get the right definitions for line and so on, are satisfied except for the parallel axiom. So maybe I'll say try to picture P of V. How am I going to picture this projective space of V, the space of lines? Well, so here I decomposed this L. We haven't come back and talked about this L. I won't. But that's another question. What does this L look like? So that's a fun problem when you think about the case when this is two-dimensional. What does this space of affine lines in a plane look like? What kind of shape? Can you recognize that? And here we have a hint because we've decomposed whatever it is by decomposing using this map. Right? We've decomposed by the fibers of this map, which I've asked you to identify. And this space in the two-dimensional case we just said is a circle. So somehow we've decomposed the space by mapping it to a circle. The projective space I'm going to decompose in a different way, different kind of general technique, and that's as follows. So let's write V as the direct sum of a subspace and the scalars. So let me draw a picture where V is three-dimensional, and so V prime is then two-dimensional. Here's the zero vector, and now we have a copy of the scalars. So we have a three-dimensional space, but it's written that way. I haven't introduced a basis, but I've decomposed it as here and here. So what that direct sum means is that every vector in this space is uniquely the sum of a vector in V prime and the sum of a vector in F. That's what direct sum means. So when we have a basis, we get numbers, and it's a linear combination of the basis elements. But if I have this, I have something that's just okay. And now I want to understand what these lines through the origin look like in this three-dimensional space, right? And so what I'm going to do is draw now a translate of V prime. So that's this one. And so that translate is going to be, so to speak, V prime direct sum, well, some element in the field, like 1. Okay? So that's now an affine copy. You see, I don't have a zero vector in there, but this is still a collection of vectors, right? And differences of those vectors are vectors in V prime. So this itself is an affine space over V prime. Yeah. So we could call that A prime. Now, what if I take a line? Well, a line in our original V is a one-dimensional subspace like that. And you see that one-dimensional subspace will intersect A prime at a point. And so it looks like we've said that the lines in V are exactly the points of A prime. Is that all right? Yeah.
One line won't be able to hit A prime.
Which line?
The one that lies inside the plane.
V prime.
Yeah.
And how many lines lie in V prime?
Quite a few.
Quite a few. So either a line lies in V prime or it doesn't. There's no in between. If it doesn't, it intersects A prime. And conversely, given a point of A prime, there's a unique line, one-dimensional subspace, that contains that point. So in other words, that says that we've written the projective space of V, one-dimensional subspaces. With this choice, we've written it as this affine space, union the projective space of V prime. Right, we've identified this with the lines that aren't contained in V prime, and these are the lines contained in V prime. And it's a union, and this symbol means that it's a disjoint union, meaning that these two subsets don't intersect. They intersect in the ends. Got it? So in this three-dimensional case, this A prime is two-dimensional. And what we've said is that this projective space looks like what? Well, it looks like this affine space, A prime, union the projective space one dimension lower, of this codimension 1 subspace. And that, we decided, looks like what? Well, those are the set of directions in V prime, right? So we could think of that set of directions as somehow being put out at infinity in A prime. Because how do I get the line in V prime? Well, you see, I take in A prime, I take a point, like here, and now take that point and send it out to infinity. Well, what happens to the line through the origin? Well, you see that it gets more and more flatter, so to speak, and it gets, in the limit, when we go to infinity, it looks like it lies in V prime. So if I were to attach this, the way the picture goes, I would somehow attach this to infinity in here. So we can think of this projective space as a compactification of this affine space. Now you could use that to try to explore the geometry of what a point and a line are. For example, if I have two parallel lines in this affine space, they don't intersect in the affine space, but do they intersect here? So you can start to explore projective geometry distinction that way. All right, so that's one kind of fun game you can have from affine geometry that leads you pretty quickly into curved spaces and so on. And projective geometry and affine geometry are two very classical subjects. Affine geometry as such wasn't really identified, say, historically until Euler, Mobius, those guys. So that's the 1700s. And right. Well, we can say other things about affine geometry. I don't know how much I'll get to other notions of parallelism. There's a choice there. But let's say a little more about affine geometry. So, again, my pictures are two-dimensional. And what I'll say now, we really don't care what field we're over, but again, we'll think of real numbers. So when we have a vector space, we have a notion of a basis. Right? So for example, well, if it's finite dimensional. So now I'm going to assume that V is finite dimensional. And we say that A has a dimension which is equal to the dimension of V. So they're both finite dimensional, but that concept comes from V. And so we have a notion of a basis. So what's a basis of a vector space? Well, in the finite dimensional case, it's an ordered n-tuple, say, of vectors, so that every other vector, xi, has a unique expression as xi1 b1 plus xi2 b2, where xi1 and xi2 are, well, they lie in the field, whatever it may be, and they're uniquely determined, and those are the kind of coordinates, what's the word, coefficient, something, for the vector in terms of that basis, right? Question?
Yeah, I just wanted to, is there, how do you define the notion of dimension for the affine space?
Well, an affine space always comes with a vector space, right? And a vector space has a dimension, might not be finite, but it has a basis that's finite. And so that's the notion we use. Good. Other questions? Don't be shy. Shyness is antithetical to learning, although difficult to overcome. All right. So I want to know what's the analog of a basis when we come to an affine space. Say in this two-dimensional case. And what's the analog of coordinates? You think about what that might be. I want to locate points. You see, we can't add points. Right? I can't add points in an affine space. I can't add 6 o'clock and 7 o'clock. That doesn't make much sense. But I can take the difference between 6 and 7 o'clock. It's a 1-hour time translation from 6 o'clock to 7 o'clock. But I could also, for example, find the midpoint between 6 o'clock and 7 o'clock. That's 6:30. So it makes sense to take a half 6 o'clock plus a half 7 o'clock. Doesn't really make sense to take 6 o'clock plus a half of 7 o'clock. But it would make sense to take a third of 6 o'clock plus 2/3 of 7 o'clock. So we'd get 6:40. Right? That's 2/3 the way from 6 o'clock to 7 o'clock. So I can navigate my clock, assuming the clock is a line and not a circle like that, I can navigate by doing what? How did I navigate?
Keeping track of your vectors, which vector you're following in V. Right?
I could try to navigate in V, that's true. But, so I could fix a point of A. If I fix one point of A, then every other point is given by a unique vector in V. So if I pick a point of A and a basis, then I would know how to navigate by giving n numbers, right? So that would be a kind of basis. But I want to navigate just using something a little more intrinsic in A. It amounts to pretty much the same thing. You see, if I give the data of one point and two vectors, then how can I recast these two vectors as data in A? Yeah.
Or you could form like a triangle in A.
So it's a triangle.
Like 3 points that don't lie on the same line.
Okay, so I could take 3 points. And those points are, in the picture you said, it's this point, this base point, and then this base point translated by each of the basis vectors. So if I have an n-dimensional vector space, I'll have n plus 1 points, p0, p1, up through pn. And now how do I navigate? How do I take an arbitrary point p and write it in terms of these points?
How far towards P1 and then how far towards, well, yeah, and there will be some linear combination that will get you to.
Okay, so I might want to write this as p0 times, let's call it a0 plus a1 p1 plus a2 p2, where again the a's are elements of ground field, like the real numbers. But what do I know about these a's? What has to be true about the a's? You see here there are 3 numbers, and this is a 2-dimensional affine plane, so I don't expect to need 3 numbers to navigate.
They should
What's
add
that?
They should add to something.
What should they add to? For example, what if it's for the point P0? What would the numbers be? 1, 0, 0. And what if it were P1? 0, 1, 0. So what should they add to? 1. So you see we're taking a weighted average of the points. And they add to 1, that's a weighted average. And in fact, if you think of this affine plane here, and imagine that we drill a hole in P0, P1, and P2, and I take, now I give you these 3 numbers. Well, what am I going to do? I'm going to take 3 pieces of string of equal length, and I'm going to put masses here of mass A0, A1, A2, and I'm going to string that thing through the table where the strings go through these 3 points. And wherever this point lands, that's the point P. That's this weighted average. So that's how you navigate. You just change the weights. We have to keep the sum of the weights constant, say 1, and then that point P will move all over. So these are called barycentric coordinates. So for example, in these coordinates, what's the equation for the line that goes through, the affine line that goes through P0 and P1?
A plus A0 plus A1 equals 1, right? Or A2 equals 0.
Yes, which is the same as A2 equals 0. So that's A2 equals 0, because this line I get my weighted averages of P0 and P1. So that's what I was telling you with my basis 6 o'clock and 7 o'clock. If I want to tell you what 640 is, it's 1/3, 2/3. That's how I navigate an affine line with 2 points. So as long as the 3 points are not collinear, no, they're not collinear, which translates to saying that if I pick one of them, say P0, and take the differences, then I get a basis of V. That's what we need. Is it time to stop.
Are we at 6?
Yeah.
Let's see. I can see if anybody's out there.
Oh, you think there's a class?
There is a class that comes in after, but sometimes they're fickle. All right. Looks like they are ready.
Well, in that case, I'll leave you with a problem, which is one of the classical theorems of affine geometry, and that's called Chéva's theorem. So Chéva was an Italian geometer that lived 1678 is when he published this. But I learned from Wikipedia, the source of all knowledge, that in fact this was published by a king, an Arab king of Saragossa in Spain, what's now Spain, way back in 11th century. So this is actually a medieval theorem. And the theorem is the following: that supposing that I have a triangle, so the way we say ABC, and supposing that I take 3 points, say P, Q, and R, and these 3 points lie on those sides. They may even spill over outside there, but they're not equal to any of the vertices. And supposing I draw these lines from the opposite vertex to those points. So the theorem is that those 3 lines, which are called Chévians, those 3 lines are coincident. They intersect in one point, if and only if the following is true: that if I take, say, AQ divided by QC times CP divided by QB times BR divided by RA, that that's 1. But what do I mean by AQ and QC? You might think I mean the length. And if we think about Euclidean geometry, then that makes sense. But we're in this affine geometry. We have no notion of length. So what do I mean by that? Well, here's the point A, here's the point C, and here's the point Q. And while this point Q, we know, can be written as lambda C plus 1 minus lambda A for some unique number lambda, right? Because those are my barycentric coordinates on this line. And so that tells me we're lambda towards C and 1 minus lambda towards A. And so this ratio, AQ over QC, is equal to what? So this is, so lambda very small means that we're very close to A. And so that would be small. Yeah, so it's lambda over 1 minus lambda. So even though those quantities AQ, this is not defined, this ratio is defined in my affine space. It's the unique lambda that does that. And so I'll leave it to you as a fun problem, which you can do using these coordinates, to prove that these 3 are coincident, if and only if this product is 1. So that's one of the actual classical theorems in affine geometry. But this notion of parallelism is something that we do in curved geometry. We have a notion of parallelism in curved geometry, but we don't usually have global parallelism like this. You see, given this line, we suddenly get this equivalence relation, this family of lines. But we have other kinds of notions of parallelism in curved geometry, but we'll have to wait another time. So, thank you.
Yeah, actually, never.